Gut, fangen wir an. Ich möchte eingangs was zur Prüfung sagen. In Anbetracht der Tatsache, dass es doch wohl nur eine überschaubare Anzahl von Prüfungsteilnehmern geben wird, haben wir uns entschlossen, keine Klausur durchzuführen und stattdessen eine mündliche Prüfung von jeweils einer halben Stunde. Ich hoffe, dass das spezifische Probleme löst und im Allgemeinen vielleicht auch Ihnen entgegenkommt, weil eine mündliche Prüfung doch eigentlich die Prüfungsart ist, die der Mathematik wesentlich angemessener ist, weil sie eben eine Prüfung auf Verständnis und nicht auf, wie soll ich sagen, handwerkliche Techniken ist. Diese Prüfungstermine können Sie dann mit mir im jeweiligen Prüfungszeitraum einfach individuell ausmachen. Okay, gut. Also was ist jetzt der Stand? Wir haben uns das letzte Mal überlegt, was das bedeutet, wie wir die inhomogenen Dirichlet-Randbedingungen einbringen und haben gesehen, im Sinne der Approximation der Gesamtlösung, also der Lösung bestehend aus der Funktion, die die inhomogene Dirichlet-Randbedingung realisiert, plus die Lösung des dann entstehenden verschobenen Problems mit homogenen Dirichlet-Randbedingungen, dass in diesem Sinne wir berechnen die finite Elementlösung, nicht plus die Funktion w, sondern plus die interpolierende der Funktion w. Das heißt, wir müssen sehen, dass dieser Interpolationseffekt keinen nachteiligen Einfluss auf die gezeigte Konvergenzordnung hat. Damit im engen Zusammenhang steht die Frage, was passiert, wenn wir die Matrixeinträge und die rechte Seite durch Quadratur auswerten. So, jetzt wechsle ich auf Englisch. And the basis for the analysis of this is the first lemma of Strang, which tells us that the picture we have with Sear's lemma is now extended in a sense that we have to deal with the approximation error of the space plus consistency errors which we get into the problem by substituting A by AH and L by the right-hand side, L by LH. And here you see these are operator norms, and here there is this infimum to be taken over all errors with comparison elements in VH. So analogously to how we dealt with the approximation error of the space, we now are free in choosing this comparison element. And again, we will try to choose the interpolant as comparison element to get an estimate for this additional error term. The approximation of these forms is, what was the other basic ingredient here in this theorem, in this lemma, was that the sequence of approximating bilinear form AH is uniformly in H VH elliptic in this sense here. In fact, this is not a big problem to justify this. We have seen, for example, there are different approaches to this, but we can, in principle, can be sure that this is fulfilled, because if we have the standard assumption that the bilinear form is V-elliptic, and we have at least some sort of convergence of the consistency error, where no rate of convergence is specified. It's only specified that this upper bound CH has to go to 0 for H to 0, then we can transfer the V-ellipticity to a uniform V-ellipticity of the A to a uniform V-ellipticity of the AH. In a second, we will see another approach, another result, which then will give us some indication how we can estimate these consistency errors. So this consistency error comes into play. Where is it? Oops. Comes into play. Why is this? I'm a little bit confused by all these things about the quadrature rules? They should. This is okay. This was in the section before. In the section before, we had discussed the quadrature rules, and we had seen typically quadrature rules. Remember the Newton-Cotes formula in 1D, which we now try to imitate in general dimensions. Quadrature rules come to existence that one says, okay, I have my interpolant, I cannot integrate it. I take some approximation, I have my integrand, I take some approximation, for example, the interpolant, in a space where I can do exact integration, and then I integrate this interpolant, for example, and getting my quadrature rule. This means one typical property which reflects the accuracy of a quadrature rule is the exactness of the quadrature rule for a space of polynomials. And the higher the degree is, the more accurate we expect this quadrature rule to be. So these are the quadrature rules we apply. So you see them here. They then pop up in terms of the quadrature points and the quadrature weights. And as we are always dealing here with affine equivalent element, it's sufficient to deal with these things on the reference element, and then the situation on the general element can be dealt with by transferring the rule, in the sense that the nodes, the quadrature points on the general elements are the transformed points from the reference element, and here correspondingly by the integration formula we get here a determinant of B into the weights. And the consequence of that is that we have this relation between the error on the reference element and on the general element, meaning that this accuracy on the polynomial space is immediately transferred to from the reference element to the general element. And also, if we have the property which we would like to have, that the weights are positive, then it's sufficient to see that the weights are positive on the reference element, because here you see it again, we only get a positive factor here in between these two things. Okay, so we have seen different examples of quadrature rules of different accuracy, the simplest one based on taking the degrees of freedom as quadrature points. We have seen in some cases we can do better in taking other quadrature points. And now we will see what the consequences of this is. Okay, so I said there's another way to see that the sequence AH is uniformly VH elliptic, and this is statement which says this only refers now to the case where we only have, so to speak, diffusive forces. So C is equal to 0. We have a little bit of Dirichlet boundary to make the problem V elliptic, and R is greater or equal to 0, not to disturb the V ellipticity. Then the situation is, if our ansatz space is pk on the element k, and the quadrature formula is exact on p 2k minus 2. This is then sufficient that in this case the AH bilinear forms are uniformly VH elliptic. So why 2k minus 2? We are dealing here only with this integral gradient of phi j times gradient of phi I times coefficient function. So if we start in this space, the gradient is then component-wise in pk minus 1, and multiplying two of them, we get the degree 2k minus 2. So this explains this 2k minus 2. And we see this immediately here. Because of this situation, because now in our discrete space, if we break this down to every element here, then on each element the formula is exact, because our integrand here is in 2k minus 2. This is a situation where, so to speak, no or only a constant coefficient appears. So in this constant coefficient situation, we have exactness, we have an equality between the integral on the element k, so integral over k, so you have to think of this term as sum over the integrals over k, and what the quadrature rule produces. But what we have here, on the other hand, is just the VH seminorm. And finally, just by applying the uniform positive definiteness of the underlying coefficient k, which is involved here in this AH, we can estimate the integral which is here, the quadrature formula which is here, which is basically the same thing as here, but instead of the alpha, we have the k times gradient of v times gradient of v. We can estimate this from below by this term. This is just the uniform uniform positive definiteness of this matrix function k. Or if it is a scalar function, it just reflects that the scalar function is bounded from below by some positive constant. So we don't have exactness for this term, but we have this lower bound, and for this lower bound we have exactness, and you see by this we have then in conjunction with the Poincaré's or with the extension of Poincaré's inequality, we see the full VH ellipticity here. Because we have a little bit of Dirichlet boundary, and this tells us, this consequence of the Friedrichs inequality then tells us we can estimate the L2 norm by a constant times the H1 semi-norm. So in fact we have here the full H1 norm. That is the reason why we need this little bit of Dirichlet boundary condition here. So this indicates that this requirement of exactness on 2pk minus 2 might be of importance, and this in fact is the situation. And so this was something what we will assume in the following, and the procedure to estimate the consistency error will be very close to the procedure which we done to estimate the approximation error between U and UH. How did we do that? So first of all, we break down from the full domain to the sum of the elements. We are dealing again with integrals or with sums over sums. And then we do the transformation to the reference element, but here no derivatives are involved in this transformation step. We only get this volume element, determinant of B, into the estimate, but we are only dealing with functions. We deal with the integrand as a function and not with we are not forced to transform the derivatives to derivatives on the reference element. So we don't get powers of norm of b to the minus 1. This is good, because that means we don't then have the problem that there are certain products of norm of b to the minus 1 times norm of b, which has to be made sure that they are bounded. So we don't need a regularity assumption. You remember, for this quantity we had the estimate 1 over rho k, 1 over the maximum, the supremum of this of the diameters of the inscribed circles, and we had to balance this with corresponding k powers, and then having a structural assumption in forms of this shape regularity telling us that we are really able to balance the rho k's with h k's. So the rho k's now do not appear, so this is very good. So in principle what we are doing here could be everything could be done without assumption of shape regularity. If that would be the case if we would be only interested in the quality of the quadrature. If we look at the total problem, of course, where we still, of course, have to estimate the problem, the error itself of u and uh without quadrature, there, of course, then we need again shape regularity or alternatively the maximal angle condition. Okay. Then we are on the reference element. On the reference element, we will do something which again applies or needs the Bramble-Hilbert lemma, and then we do the back transformation step. So it's very similar to what we did up till now. And the important thing is, in the moment we are on the reference element and we are dealing with this finite dimensional polynomial space, which we use as approximation space of a reference element. We have a space of a fixed dimension, depending on what we are doing. Dimension 3 in the case of linears, in 2 space dimension at a minimum, and so on. But on this space, we can take advantage of that on a finite dimensional space, all norms are equivalent. Of course, with equivalency constants, which depend on the dimension, but these dimensions are fixed, typically small numbers. So on this space, we can substitute what we can estimate, say, an H1 norm by an L2 norm, which of course in general is wrong. This is due to the finite dimensionality of the space here. Okay, so in the following we will need a little bit the general Sobolev norms. So not only the HLs, but the HLPs, and in particular HL infinity, P equals infinity. With here the corresponding notation globally on the element and the semi-norms. So, okay, this is the statement we would like to prove. So we assume that we have on the reference element, so we apply the same quadrature rule. So we're talking here only about the volume integrals, and correspondingly for the surface integrals, we have to do the same thing, just one dimension lower. So for the surface integrals, it would be, for example, if we look at the triangle with a linear ansatz on the surface, for the surface integrals, so the integrals over the edges, we would then have also linear ansatz there. So it would be the same k, and the same applies for all our other elements. So the requirements is basically the same also for the surface integrals. Of course, they have other reference elements here. In this simple situation, linear ansatz on triangles, our k hat is the reference triangle, and the k tilde hat or whatsoever, the reference element for the edge is just the interval 0, 1. Okay, so we assume that these quadrature rules we apply are exact on this polynomial space pk minus 2. This is stated here. And the assertion then is, and it's written here a little bit redundantly to see the applications we would like to do is, so here we always have now these errors between the exact integral and the quadrature rule, so to speak, for different compositions of the integrand. And you see here a little bit, I hope the notation is also done like that you see to which terms in the bilinear and the linear form this relates. So what do we have? Let's look at the first case. In the first case, P and Q are polynomials of degree k minus 1. So this appears in the first term, where we have gradient times gradient. And then what we have in front there, so in the application we have to think of a component-wise application. We have here the corresponding component of the coefficient function. So for this function a, we have to require that this function is in wk infinity. So it has weak derivatives up to order k. This is the k from here, and from here. And all the derivatives have to be bounded. That is the requirement. That is also what we used in showing the v-ellipticity for the continuous problem. If we have the situation of a triple product, and we have two factors which fit together in the sense that they produce an L1 function, this next one has to be then an L infinity function to keep the integrability of the whole thing. So this is quite natural that we have to have this assumption, and what comes out in this case we can prove. That is the assertion that we can estimate here the error of the approximation of the quadrature rule by a power hk to the L. So L is either k, so we have here capital K and small k, hope this is no problem. But then we have to use here the k minus 1 norm for the one factor, always the 0 norm for the other factor. And if we only want to have only the 0 norm here, then we also get an order of convergence, but the order of convergence is then only 1. And the other results are basically of the same feature. So here, for example, we have Q from pk, P from pk minus 1. So this reflects the non-symmetric advective part with one derivative and one function with no derivative. And you see what comes out is the same thing with a difference that here for, where we are, here for the function which do not appear as a derivative. So here we have to think of a derivative. So here in fact we plug in a derivative. So here the derivative, the L2 of a derivative appears. That is something like an H1 seminorm in the end. And here we plug in a function. So again, the H1 norm appears. So the outcome in the end is of the same type here. And finally here, so this was number 2. Number 3, we have P and Q from pk, so no derivatives involved. Therefore here also the 1 norm, and here then correspondingly not the L minus 1, but the L norm. So we have here to have a 1 norm to get an order 1. And a k norm to have an order k. So this was for the 3 ingredients of the bilinear form, the volume integrals in the bilinear form, and this is for the corresponding right-hand side. Here the f is fixed. It's not from a finite dimensional space, better to say. And here the q is just a function, therefore from pk. And here the estimate changes a little bit. Here again the 1 norm. Here we get in addition the square root of the volume of k. And so this enhances, so to speak, a little bit this order estimate here. Okay, the proofs are, on the one hand side, the proofs are quite similar of the 4 assertions. On the other hand, if you go into the details, the proof of 2 to 4, or at least 2 and 3, I do not really remember, are more complicated than the proof of 1. In the sense, if we would do exactly the same proof of 1 as in 1, we would lose order of convergence. So there further tricks have to be involved. I'm not going to go into these details. I'm only going to show the proof of number 1. And for the rest, you have to believe me. I hope at least it's correct. Okay. What's the other things I said already? So the major thing is that on the space pk, k hat, as a fixed finite dimensional space, we can renorm as we like. Okay, so let's start. So we have a general element k. We have the coefficient function a from wk infinity, and we have these 2 polynomial functions pq from pk minus 1. Correspondingly to these functions, we have the transferred functions on the reference element, which do not change their regularity and do not change their polynomial degree, because we have an affine linear transformation. And we had two assertions, the one for the high regularity with a high order, and the other one for the low regularity, and the other one correspondingly for L equals 1. So we start with L equals k. So let's look at now we are in the reference element, and we know, so the difference between the error on the reference element and on the general element is just the determinant of B. That was something which we remembered. So look at the situation of the reference element. So here we have the integral, here we have the quadrature rule. The first assertion is that we can, and that is what is here behind. What I just mentioned is what I said. By the transformation, we don't get powers of norm of B, and we only get determinant of B. Now we have to deal with on the situation of the reference element, and the first thing is to see that what we have here. This is a functional. It's a linear functional in Q. So we consider the V hat to be fixed, and then we have here a linear function and here a linear functional in Q. But it's not only a linear functional. It's also a continuous functional, because what can we do? Of course, this here we can estimate by the maximum norm of the integrand times the volume of k hat. This all vanishes in this constant c. And correspondingly, we can estimate these pointwise values by the maximum, and then the sum of the omega L hat remain. This is also a constant. Actually, this is the volume of the reference element, what we have seen already. So we are here. The next trivial step is, of course, we can estimate the infinity norm of a product by the product of the infinity norms. So this tells us that, so the question is, does this make sense here? Do we have an infinity norm of the function v hat, which is in wk infinity? But our general assumptions told us that if the k is, as in our case, greater or equal to 2, I'm a little bit confused. If the k would be greater or equal to 2, then in any case we would have this continuous embedding here. And as we don't have here a 2, but an infinity, we can relax a little bit. So we have to refer here, this requirement k greater or equal to 2, there's of course something we would like to have. So what we need here is something what we do not have stated explicitly. There is a refined embedding theorem, not only dealing with wk2, but with wkp. And in general, it's like that. These embedding theorems are pretty easy to remember. So what one does is one loses the order of approximation which one loses is k divided by p. So k divided by p formally is here 0. So that tells us everything which is below k is okay for a space of continuous functions. So k equals to 1 would be okay here. In any case, we have this continuous embedding. Tell us that this is okay, what we are doing here. And now we are taking advantage of this equivalency of the norms. So here in the second component, in the finite dimensional component, so we just say the infinity norm is equivalent with the L2 norm, which of course in general on the infinite dimensional space is nonsense. So we get the L2 norm here. This tells us this functional which we have here, this functional E hat, as a functional in Q hat, is a linear functional from the L2. Okay. Now, sorry. I have to, we do not consider it as a functional in Q hat, we consider it as a functional in V hat. So it's a linear functional from WK infinity, which is continuous, but what we have seen here is an estimate for the norm of this functional in terms of the C times the L2 norm of Q hat. So this is the situation. So now the question is, can we get rid of this full K infinity norm? And by means of the Bramble-Hilbert lemma, we know we can do so. We can substitute by maybe increasing the constant C here, this term just by the semi-norm K infinity, under the assumption that this functional vanishes on the corresponding polynomial space. But this is the case. So this is what we have seen. If we call this functional G, we have seen its norm is estimated by constant times L2 norm of K hat, of Q hat. And now if we plug in pk minus 1, so what does that mean? If we plug in pk minus 1, so we have here an element from pk minus 1. The Q is an element from pk minus 1. So in total, 2k minus 2. And that was our assumption that the formula is exact on this space. So that means we know that this polynomial space belongs to the kernel, and that was exactly our assumption in the Bramble-Hilbert lemma, telling us, as I said already, we can substitute here the full K infinity norm by the highest order semi-norm. Okay. So this is the situation on the reference element. You see, we did exactly what we have done in the order of convergence estimate. Now we make this more, we try to apply this, and for the function V hat, we take A hat times P. A hat is the transformed, say, coefficient function, and P hat is also an element of pk minus 1. So the problem which we now are faced with, we have to estimate this highest order semi-norm. Only the semi-norm due to the application of the Bramble-Hilbert lemma, not the full norm. That is now important. So we have to look at derivatives of this product here, all of the order k. And you remember Leibniz formula, the Leibnizsche Regel, which tells us something about the iterative application of the product rule, tells us how to compute a higher order derivative of a product. And you remember what we get is a sum with the binomial coefficients, and then these combinations of derivatives where the orders always add up to the order of derivative which we would like to do. So it's, in some sense, it's the formal application of the binomial formula. Okay, so this means that we can estimate here, remember this k is also a fixed quantity here, so the c is allowed to depend on the order k, so all these binomial coefficients are allowed to vanish here in the constant, and what we are left here are products, as I said, of derivatives, where the order of derivatives add up to k. So if we estimate the maximum norm, we can just first apply the triangle inequality and then estimate the maximum norm of the product by the product of the maximum norm. The next observation is, here the sum goes to k. So we have here the kth derivative in the last summand, and here the zeroth derivative, so the L2 norm. But actually this term we do not have, because our element here is in pk minus 1, and the kth derivative of this polynomial is just 0. So actually the sum only goes here up to k minus 1. So what does that mean if we plug this in? So we have this estimate, so we have C times L2 norm of Q hat. So this is this, and this is just the estimate we have seen right now for this remaining product term. Okay, so what do we do here? Yeah, okay. Now again, we take advantage of this equivalency of norms. We estimate the semi-norm in J infinity by the semi-norm in J2, Wj2, which of course in general is also wrong, because it means to estimate an infinity norm by an L2 norm. So this is this equivalency on the finite dimensional space which we apply. So now we have to go back. We have to go back in the transformation here. Here's no problem, no derivatives appear. So what do we get in going back? Here we just get the 1 over the square root of the determinant in going back. This factor we get here also. And the power j. Here we get correspondingly the power k minus j. But as we have here the infinity norm, and the general formula applies here minus 1 over p, that means the determinant part is not present here in this part. P equals infinity, 1 over infinity equals 0. So, okay, this is now nice. So these things go together. This gives us the order k as we would like to see that. This gives us a determinant to the minus 1, but we have had a determinant from the first transformation, so these terms just cancel, as we had it also up in the order of convergence estimate. So we are now on this level here. So we have seen the order k, which we would like to have. We have here our L2 norm, and now we have here this estimate here. And we see what we have here. This can be estimated. Maybe we go back to see the assertion, what we had. How was the assertion? The assertion was that we can see here the ck to the k. We have here the L2 norm. For the A, we have the k infinity norm. For the B, we have the L minus 1 norm. And that's exactly the situation here. Namely, where is it? Okay, if we now estimate all these terms, they go up here. Let's start with this. This goes up to k minus 1. So all these semi-norms can be estimated by the full k minus 1 norm. And these are here in between k for j equals to 0 and 1. So this can be estimated by the full k infinity norm, all these terms. So this gives us the assertion for the case L minus 1. Now we need the variant for this lower order estimate, only having here not a full k minus 1 norm for the p on this side, but only an L2 norm. So we go back to this estimate. Maybe it's easier to do it. Let me do the fancy tricks here. We go back to this estimate here and see what we have to change. So what we do not like to have are these higher order norms here. But that's no problem, because here we can equally well use the equivalency to a lower order norm. For example, the L2 norm. So let's do this, and then we end up with this estimate here. Of course, we would not be able to do some tricks like that with this term, because this element is from an infinite dimensional space. But here on the fixed polynomial space, we can do that. So we estimate this norm by the L2 norm. We get, see this term here. And yeah, then we are more, now we have to see this order still. That is, we have to do a back transformation. And how is it? So by the back transformation, we get here corresponding orders of k minus j. But now there's no order of j here which add up to the order k. We only have here in the sum k minus j. So the best thing what we can do is to take the lowest order which we get, and the lowest order which we get is for k minus 1. Then k minus j is k minus 1 is 1. So the lowest order of in h which we get from the back transformation is just 1 power of h. And so we end up with this 1 power of h. We end up with this sum of the semi-norms now back transformed. Here everything is okay. The determinant terms have cancelled again. And this term again can be estimated by the corresponding full k infinity norm. This gives this variant of the estimate. So now let's see what we can do with that. And this is the theorem. I do not claim that this is an optimal theorem. In fact, these things are not so clear if you look at other books. Of course, our book is not the first book which was written about that. And of course, we have looked at the other books also. If you look, for example, in the famous book by Philippe Cialet, maybe the most famous book on finite element analysis, you will not find these things very explicitly there. So this is an explicit statement which maybe is not the optimal possible, but let's see what I mean with that. Okay, so what is the situation? We consider a family of affine equivalent Lagrange elements. In Rd, d less or equal to 3, that we are fine with the embedding. We start with at least with k equals to 1. And finally have the requirement that the solution is in hk plus 1, so at least in h2. So we have continuous function, everything is fine with the embedding and the interpolation operator, which we need for our purposes. So then we need some requirements on the structure of the triangulation. Either we require that shape regular, or equivalently, we can require in the case of triangle with linear ansatz, we can require the maximal angle condition. Because this additional analysis part which we now did concerning with the quadrature error did not need any of these assumptions. Okay, so then this is, maybe it's not so nice in the formulation, but in the end it doesn't play a role. Now we For doing this transformation of the problem to fit it in our Galerkin, fit it in our variational formulation, our Galerkin formulation, we had to have this function w fulfilling the inhomogeneous Dirichlet boundary conditions. For this function w, we now for this formulation, it was only necessary that w is an h1 function. Now you will see that we need a little bit more. We need that this function w is also in hk minus 1. And on top, of course, the solution of the transform problem with the 0 Dirichlet boundary conditions also in hk plus 1. Of course, one could now say this is now too much. Actually, what should be the requirement that only the sum u plus w is in hk minus 1. But we discussed how to select this w, and the point is, of course, if there is a solution, of course, then there is also a w is a solution fulfilling this requirement. Then, in particular, there's a w fulfilling this requirement, because then, if one would have to know the solution, one could choose w as the solution, and the remaining homogeneous problem would be just trivial with a 0 solution. So there's no restriction here in this requirement. it only feels a little bit, at least for me, it feels a little bit suboptimal. Okay, so these are requirements, and now the statement is there is a constant, and there is a constant h bar for the fineness of the triangulation, independently of the solution u and of the w, such that the finite element approximation we are going to approximate. So this is the WH, which we get by our procedure to deal with the Dirichlet boundary condition, and correspondingly the UH bar, which we get then by solving the resulting set of equations, that this finite element solution fulfills the following error estimate. So this sum is an approximation of the full solution of the u plus w of the order at which we have seen. We have no reduction in the order. Of course, we need a requirement on the quadrature formula, which I do not have stated, but of course now it should be clear. The requirement which we are going to do is that the quadrature formula are exact on pk minus 2, which is not very much. Look at the linear ansatz. That just means that the quadrature formula has to be exact for constants. So we could take a one-point quadrature rule and everything would be okay in the sense of this order estimate. Maybe one will be a little bit more cautious and say, okay, I invest a little bit more in the quadrature rule, but it need not be very much. Or for k equals to 2, for quadratic ansatz, we have then here 2 times 2 minus 2. We have just be exact on this ansatz space. So it's not very much. So what comes out is basically the same error estimate. The only thing what changes a little bit are these terms, these norm terms which appear here. So we have the k plus 1 semi-norm term as we expect, or as we had seen already. So this, of course, we do not get rid. We have now, in addition, the k plus 1 semi-norm term of w. And here correspondingly the k infinity term of f. So that means, in addition, we need more regularity for the right-hand side. So it's not sufficient that we have just L2. So this is a little bit of drawback here in this statement. And here, furthermore, we have a term, an additional term, which deals here with the full norms. But this I would not deal. So we can, in general, we can either estimate those norms nor those norms. So it's just a qualitative statement. Of course, this is a further requirement. We have to see where this comes in. So let's look at the proof. So what we have to do, according to our considerations before, we have to estimate this term here. So the full solution with the approximate solution which we would get if we would, so to speak, transform the discrete function by the interpolant of the w. We know that this sum of discrete functions is just the sum of the discrete functions we are computing. It's just this sum here, the UH bar plus the WH. Okay. So, and this IH bar, this indicates that, so the problem is formulated, the transform problem is formulated with homogeneous Dirichlet boundary conditions on the Dirichlet boundary, but here we have to apply the interpolant operator, so to speak, ignoring the Dirichlet boundary conditions. Here also the Dirichlet nodes are degrees of freedom. This corresponds to our algorithmic procedure in incorporating the Dirichlet boundary conditions, first forgetting them, setting up the equations, and then bringing them in. Okay, so what do we know is we know an order of convergence for this interpolant operator, which is of order of order h, and here you see where this comes in. Of course, here now the k plus 1 seminorm of W comes in. Okay, so to apply the lemma of strength, we have to estimate the consistency error, so we have to start in estimating these terms here. And we have the freedom to choose, so both for the finite dimensional space, otherwise the AH would not be defined at all. For the V, we have the freedom to choose the reference, the comparison element, and we will then later on choose the interpolant. In the W, we have then go to the maximum in this estimate. So let's look what we have. So we have done here, you see already, so what we did here already is an estimate going, so to speak, in the products of the integrals and estimating each summand, the modulus of the whole thing by the summand of the moduli. So we get here the corresponding errors by the terms which appear in the first integral, Kij, J derivative, I derivative. Here corresponding we have the Ci, only one derivative. Here we have the R and no derivative. So these terms are now of the form which were dealt with in our preparating theorem. So we can get out of all those terms an order of HKL. Here the corresponding norms of the coefficients, so basically the WK infinity norms. And here in the sum, the W in W the 1 norm, and here the L norm corresponding, or whether we have L equal to 0 or equal to K. Again, why the 1 norm? Let's go back to, I said it already, but let's go back again to this point. Why the 1 norm? Here we have a derivative, so we have an L2 norm of a derivative. Here we have just the function, so we have the 1 norm, and correspondingly here we have just the functions, therefore the 1 norm. So we have now this type of estimate, and now we can go on. You see here this is a large sum. This is something like a scalar product with the index k. So we can apply here Cauchy-Schwarz inequality. This gives us, this gives us, so to speak, the corresponding norms built up of the norms here on the elements. This gives us this term, and this is an upper bound for all these coefficients coming up here, and here we just also go to the upper bound by taking, instead of hk, the maximum. Here we have to be a little bit careful. Our function, our polynomial function is, in any case, our polynomial function will be in h1. But depending globally, so our piecewise polynomial function will be in h1, because we have seen h1 is, global h1 property is equivalent with the continuity property. But here the situation is a little bit different in the sense now we have a higher, if the L is equal to k, we have a higher order Sobolev norm. So on each element, of course, this is okay. On the element, we have a polynomial, so every power L is allowed. But in general, it's not allowed. We have continuity across the boundaries, but not continuous differentiability or higher order continuous differentiability. So we have to stay here with this, what I called already the broken Sobolev norm. So we have to stick to this. In this formulation, we cannot put it together and say, here this is the L norm on omega. So, okay, now let's look at the estimates. First, for L equals to 1. So we get only the power 1 here, and then this problem with the broken Sobolev norm does not appear, so we have here just the 1 norm. But this tells us that the lemma, which we had before, which told us how to transfer the V ellipticity of the form A to the AHs, this is now applicable. So this was this requirement for the consistency error. Our norm is the one norm, and here our CH is in particular C times H already. So this is here a quotient. This is a supremum over a quotient. So this is the second factor here, which is divided off. So exactly this term remains here in this estimate we have just shown in the form C times H, with a constant C times H. So in any case, this is fulfilled here, and that means if we choose the H small enough, we can be sure that there's uniform VH ellipticity. So that was the one requirement to apply the lemma of Strang. So this is stated here. Now we estimate the consistency error with the aim to get the full order of consistency. For this purpose, we are now allowed to choose a specific comparison element from VH, and we select again the interpolant, as we did this already. Of course, we have to assure that the interpolant is allowed to take, that we can, no, let me phrase it otherwise. What does that mean? We have here, now we have chosen the V specifically, and so we have to deal with this broken K norm here, L equals to K, small k. So let's estimate this thing here. The first thing is independent of the norm. Of course, we can estimate the norm of IHU by the norm of U plus the norm of U minus IHU. For the U itself, we have required that the element is in HK. So the broken norms go together to the global norm here. And what we have here, we have now the interpolation error. But according to our estimate, we get here at least an order H times the K plus 1 semi-norm of U, which again, and all these terms can be, the H can be estimated by a constant. And here, everything else can be estimated by U in the K plus 1 norm, so this term actually can be estimated by the K plus 1 norm. So now this means the consistency error is exactly what we would like to have. Let's look again. So what we have seen, we have estimated this quantity here by choosing the V specifically as a specific element. We get here the right order K, H to the K, we get some factor. Here we have seen we get the U corresponding to our choice of the V, our solution U in the K plus 1 norm, and here we have the 1 norm of this discrete element W from VH. So if we now divide this quotient by the norm, then we have still this estimate here. Taking the supremum over all the W's, we have still this estimate. And by selecting this specific element V, we have now an estimate for the infimum over those in V now over those quantities over this operator norm of this quantity. And this is exactly what we have in Strang's lemma. Let's go back to Strang's lemma. So what did we have here? Oops, this is not the statement here. So here you see we have an infimum over the V. This infimum we can estimate by choosing a corresponding V. We have to choose the same V here and here. Here we did it already. We have taken the interpolant. Now we've taken the interpolant here. So we are left with this term. So for this difference, we had an estimate with norm of W. So if we divide by norm of W, this is gone. And we have a uniform bound in W, which then also applies to the supremum. And this uniform bound is what we have got now out for this term here. So here we have already seen, this is our old estimate, the ck times semi-norm of u in the k+1 order. And for this term now we have seen what we would like to see, also h to the k, but the factors are a little bit more involved. They include all the L infinity, all the wk infinity norms of the coefficients, and they include, let's see where the statement is. They include all these k infinity norms of the coefficients, and they include the full k+1 norm of the solution. So the terms we have dealt with up till now has given us this part here. This is just the order of convergence estimate without any approximation and quadrature. This term, the additional the additional interpolation problem which came in, and this times this term. So these terms are now are already in the estimate. So what is still missing? What do we still have to estimate here? Is the right-hand side. Let me see. So we are here. Now the consistency error is okay. Now we have to look at the right-hand side. And in the right-hand side, two things come together. The one is the error which we do in the evaluation of the right-hand side by quadrature. This is this part. And the error which comes in by our specific treatment of the Dirichlet boundary condition. This is this part here. Let's start with this second part here. And okay, we can estimate this, but just by bringing in an additional term and subtracting it again. This is this term here. Here we have both effects. We have quadrature plus interpolation, and it's quite obvious that one tries to separate this. So here we have only quadrature, and then here we have only interpolation, and then here we have the quadrature effect. So what can we do for these summands? So for the first summand, we can just estimate by the continuity of A by W minus the interpolant in the one norm times V in the one norm. So that gives us, so this tells us, okay, we get again here the interpolation error in, for now applied to the W. And so this term we divide here if we look at the operator norm, and then we have to only to estimate this term here. And this is just the interpolation error. So this brings in, okay, let me go back, it's a few pages, but this brings in this term here. Oops, where are we? Then we have this part here. So this is again now the question, how good is the quadrature? Now also for a slightly differently chosen comparison function, namely here the interpolant including the Dirichlet nodes. But if we go through what we did, this doesn't play a role whether the Dirichlet nodes are included here or not. So we have exactly the same estimates as we had before here. Now, the function is not u which gets interpolated, but it's w. That means we get the whole thing again in the estimate, but not now for the u, but for the w. So now the only thing which is left to do is to deal with the, oops, what is this here? To deal with this term here. B minus BH. And this is, I guess, a misprint. This should be really BV minus BH of V, so the H is on the wrong place. It is nonsense what is noted here, so the H has to be here. So we do again the same play with the quadrature error, go to the elements, do the transformation, do the back transformation, and then maybe I skip this now, we get this term here. And here's the place where now this high order requirement for the right-hand side comes in. To take advantage of the corresponding order of corresponding approximation order of the quadrature rules. It's clear, all these estimates we have, there's always an interplay between regularity and amount of order which comes out. To have a more advanced formula requires that the quantity which is approximated has more regularity to take advantage of this more advanced approximation. Okay, so in this sense we are now really done with the a priori order estimates. We have included everything what we are doing, and this assures us it's okay under two requirements, namely, of course, the solution has to have the regularity. If we go into higher order approximations, we have to have solutions of this regularity, and this is a wide area also of interesting numerical experimenting to see is this only theory or is this also praxis. And what is typical is, as we have seen already for example, with examples with re-entrant corners, that if there is a decrease in regularity, this is only locally. So the question is, if this order of convergence breaks down, does it break down globally, or does it only break down locally, or does it do not break down? So hopefully we will have the time to do a little bit of these experiments then by means of the code you are in the process of writing. Okay, and the other thing is, of course, we have to take the quadrature rule appropriately, but the requirement is not very high with this accuracy of 2 exact for polynomials of order 2k minus 2. Okay, so you see we have still now 3 smaller chapters, 3 smaller sections in this chapter, and then we are done, and then we can relax and look at iterative methods for a while at least, before we come back to discretization methods. And in preparation of this, we will now look at the condition number of the matrices which appear. If you have dealt already with linear sets of equations, you will hopefully know the notion of the condition number of the matrix. And the condition number tells us something how stable is the solution process. This is independent of the stability of the method we are using. This just reflects the stability of the discrete problems, which of course is again related to the stability in the sense of the ellipticity of the continuous problem in our case, because our sets of equations are not just black box models, they come from something specific continuously. So the condition number is important, and let's both for all kinds of solvers, so let's look at an estimate of the condition number. So what kinds of matrices we have to look at? So the one thing is the condition number of the stiffness matrix. So bilinear, so we now neglect all these effects we have now analyzed, all these quadrature effects, we go back to the original form and assume that the form is exactly evaluated. Of course, we can expect by our consistency results now that because we are changing the matrix only slightly, the condition number should also change only slightly, in a certain order of h, by our quadrature effects. But that isn't, we are not going to analyze this now in detail. We only look at the original formulation of the stiffness matrix, take the bilinear form, plug in the basis function, that's it. There's an additional matrix which plays an important role and which will later on come up when we look at time-dependent problems. That is the so-called mass matrix. In the mass matrix, we do a similar thing. We take again the basis functions, but we only apply the L2 scalar product. And we will look at various relations between A and B, and in conjunction with that, try to estimate the condition number of A. That means, of course, we have to fix a norm to do so, and this is important because we are not looking at this problem as a finite dimensional problem. It's not a fixed m, it's an m going to infinity, it's an h going to 0. And therefore the choice of the norm is of importance. It's not the same, we do not get out the same thing for the same norm. So what we are now going to do is we choose the spectral condition number. So we take, for the tuple space, we take the Euclidean norm, and correspondingly the induced norm is the spectral norm. And to remind you what the spectral norm is, in general, the spectral norm is the spectral radius of A transpose A in the square root of this number. But here, in both in the situation where we have a symmetric matrix, so in B in any case, and A, of course, this depends whether small a is symmetric or not, then this quantity I just defined reduces just to the spectral radius. This is the spectral norm to the spectral radius of the matrix. So this is the spectral norm. Now what is the condition number? The condition number is the product of the matrix norm of the, say, matrix A times the matrix norm of A to the minus 1. And so in the symmetric case, this just means modulus of the largest eigenvalue divided by the modulus of the smallest eigenvalue. And what is typical for our situation here, because there are approximations of the corresponding continuous situation, so our eigenvalue problem is, so to speak, an approximation of the eigenvalue problem for the elliptic operator, is that we have a positive lower bound for the lowest eigenvalue and the largest eigenvalue, because we're getting, if the m increases, of course, we're getting more and more eigenvalues. In particular, in the symmetric case, then we have real eigenvalues. The largest eigenvalue goes to infinity in modulus. So that means the quotient gets worse and worse. And this is something which we expect to be reflected here. And let's see what comes out. Okay, so what we do here to simplify the situation again, we only look at Lagrangian elements, we assume the affine equivalency of all elements we are looking at, and we assume that the family is regular. And further on, we assume that the underlying bilinear form is V elliptic. So let's start with some preliminary consideration, in the sense that we define something like a discrete Euclidean norm on our finite dimensional space. So our finite dimensional space is represented, so this is supposed to be the nodal basis, phi 1 to phi m. So our finite dimensional space is represented by the values at these Euclidean, at the corresponding degrees of freedom, which here are denoted by AI. And of course, we can say, this is a function, of course, but it's also represented just by this vector. as in the finite difference sense. And in the finite difference situation, as you remember, we said, okay, we build an Euclidean norm out of this vector, but we should be careful that it to make that the thing makes sense. At that time, we were in 2 dimensions. We should multiply everything with h. Here we do something. Here we do something which looks a little bit similar. So what do we do here? We go over all elements. We sum up the squares of the values of all the corresponding degrees of freedom. Multiply by hd, multiply over sum over the elements, and then take the square root. So if all the hk would be the same, so we would have here h to the d half, so that would be just our h in the 2-dimensional case. Nevertheless, this is not really this weighted this discrete L2 norm or this weighted Euclidean norm we have used in the finite difference settings. Do you see the difference? Do you see what is the difference here? Yeah, the difference is, of course, we're going over the elements, and then on the element we touch each degree of freedom. So each degree of freedom is touched several times. But in general, we have no control how many, because depending on our, in general, unstructured triangulation, a node can belong to 5 or to 20 or whatever number of elements. And this is the amount as this value appears here. So in general, it's not so clear what the relation of this norm is to this norm which I described, and this apparently has something to do with the regularity of the triangulation. That is the first thing what we would like to analyze. Okay, so first of all, is this a norm? Yeah, this is a norm, of course. Yeah, the norm properties are clear, maybe up to definiteness, but definiteness just means if all those quantities at the degrees, if the function vanishes at all degrees of freedom, it has to vanish, and this is just the uniqueness of the interpolation problem. And this is the why did we define this norm? It's simple to compare with the L2 norm. The first statement is this norm, which we have thus stated, is equivalent to the L2 norm on each VH. That would be a trivial statement, because on VH all norms are equivalent. But the equivalency constants here are independent of H. It's a uniform equivalency. That is the one thing. And as a consequence of this, we will see that on VH we can do something which we cannot do in general. Maybe this enhances this, what I have said now several times. We can estimate the one norm by the L2 norm. Of course, in general, this is nonsense. And here you see the price we have to pay, so to speak, the dimension-dependent price we have to divide by 1 over the minimum of hk. That says, okay, there is a constant h-dependent, but it's getting worse and worse the smaller the h gets. Okay, and then later on, of course, we have to see how this norm relates with more standard norms. So let's do that. And yeah, we do this as we do it all the time. We break up everything to sum over the elements. We transfer to the reference element and see what we do. So, okay, we are on the reference element. And on the reference element, we know that all norms are equivalent. That means on the reference element, the Euclidean norm is taking into account the values at the degrees of freedom, is equivalent with the L2 norm. This is specifically for the reference element. Now we do the transformation, and in the transformation in the volume we get the determinant of B in, and now we take advantage of the regularity of this family. That means if we take up, we have constants here such that hk to the power d can be estimated up to a constant to rho k to the power d. But this, the constants can be made, the C3 tilde can be chosen like that here we have a lower bound for the determinant of B. Again, what was the determinant of B? This is the volume of the parallel epipet spanned by the columns of B. And what is this? This is then the diameter of a ball lying in this parallel epipet, and then of course in each direction then the surface, the volume of the ball, which is proportional to diameter to the d, must be smaller than the volume of the full parallel epipet. Everything up to constant, so all this nice pi times whatsoever goes into the gamma 3 tilde here. You remember pi times 4 over 3 in 3 dimensions and so on. I have to do this now with my daughter all the time. In the 10th grade, you have to know something about the volume of a ball in 3D. Okay, so we need an upper bound. We have a parallel. This hk is now the diameter of the element, so each of these x's given by the Euclidean length of the columns of the matrix B can be estimated by hk, and then of course this is an estimate of the volume of the parallel epipet here. So we get this estimate here. So this tells us, as a consequence of the, this is now independent of this is a general statement, as a consequence of the regularity of the family, the determinant of B behaves like the dth power of hk here. This is this statement here. So now let's see what we can do with that. So we start with the L2 norm. We do the transformation. We, for the determinant, we estimate with this factor times dth power of hk, as we have seen. Here we use the equivalency of the norms. Now this thing goes together, and that's the way it was made, exactly to form our new norm here. So this is the first estimate. Now we have to go in the other direction. Then we break this up again here. Why is this here? Yeah, okay. Then we break this up. Let's just get this factor out of here. We are here. Here we again use the equivalency of these two norms on the reference element. Now we go back. We get this factor in. And now we again use the equivalency of the determinant of B with the dth power of hk. So this term cancels with this term up to some constants. We have some constants times the L2 norm. So this was now the first assertion here. The uniform equivalency of these two norms. The L2 norm and this h-dependent new discrete L2 norm on the VH. Now, what can we do now? Can conclude the second result. We do basically the same assertion, the same argumentation, and on P hat we are allowed to do everything, as I now said 1,024 times. So in any case, we can also say the 1 norm is equivalent with the 0 norm. So what does that mean? So yeah, what do? We estimate first the 1 norm by the 1 norm on the reference element. This brings us these factors. Then we substitute, by this argument I just mentioned, the 1 norm on the reference element by the 0 norm. Then we transform back. Now we have the 0 norm. That means no powers in a norm of B. Only the determinant part, which cancels with this part. Now we are left with this thing, which can be estimated to 1 over hk, and this gives us, if we now go here to the minimum of these quantities, we have just the inequality asserted. Something like this here is also called an inverse Sobolev inequality. It's an embedding in the wrong direction, so to speak, which can only work on finite dimensional spaces. Okay, so this was now the preparation. Let's see what we can do with that. The problem to compare this norm, which discrete norms we already introduced, as I said already, is the problem that we do not, in general, we do not know how many, if we look at a specific node, how many elements does this node belong. That is, how often this ingredient is counted in the discrete norm we have introduced. But now, with our assumption of the to handle this problem, we make the following assumption. We assume that there is a constant CH independent of CA independent of H, that for each node, the amount of elements to which this node belongs is bounded by CA. This is a partially redundant requirement because in the two-dimensional case with triangles, we had analyzed the shape regularity and had seen shape regularity is equivalent to a minimal angle condition. But if we have a minimal angle condition, that also tells us there's an upper bound for the amount of triangles which can share this specific node. So in the two-dimensional case with triangles, it would not be necessary to do this assumption. Okay, now we work with this assumption. On the other hand, if we would like to work with a maximal angle condition, this would not prevent us from having this increasing amount of elements around a node. So that here, then it's really an additional requirement. So again, let us remind us a little bit of linear algebra. If I have a matrix with real eigenvalues, let's say ordered from 1 to m, 1 is the minimal one and m is the maximal one, and let's assume that we have an orthogonal basis of eigenvectors, so we can be sure that this situation holds true if our matrix is symmetric, or in general, more general, if it's normal. Then you maybe have seen this quantity already. That's the so-called Rayleigh coefficient. And so what do we have here? That's a quadratic form defined by the C divided by the Euclidean norm squared. And the assertion is, which is pretty simple to show, so this quadratic form, you should now protest why I call this a quadratic form. It's a quadratic form over a quadratic form. But let me make a comment on this in a second. This term can be estimated from above. So this is not only an upper bound, it's a maximum by the maximal eigenvalue, and from below by the minimal eigenvalue. And it's attained, those minima and maxima are attained for the corresponding eigenvectors to these eigenvalues. So why can we call this still a quadratic function? So equivalently, we could say, instead of, say, looking at this, for example, if we look at the minimum problem coming to the lambda 1, the minimization problem, or the maximization problem coming to the lambda m. Instead of looking at this quotient, we could say we look only at the quadratic part here, so the upper part. But in addition, we require that, you see here orthonormal, we require that the Euclidean norm of the vectors is 1. So we do the maximization and minimization only at the surface of the ball. This is a nonlinear constraint, but it's for a quadratic function now. So this is the connection between eigenvalues and Rayleigh coefficients, which we take advantage of now. That is, if we now going to estimate, so in the case of the symmetric matrix, that is, for example, in the mass matrix, we want to estimate the condition number. That is, we want to estimate the quotient lambda m over lambda 1. We have to find upper bounds for lambda m and lower bounds for lambda 1. And this we do in terms of this in terms of this relation here, because if we found an upper bound for this quotient here, then we know that the maximum, the best upper bound, is below this upper bound, and if we find a lower bound, then we know that the best lower bound is above this lower bound. So this is the procedure now, and by means of this procedure, we are going to prove that we have the following estimate for the mass matrix. So the assumption now is, it's a little bit of cheating, I have to admit. So what we are now going to say is we assume that this property holds. And I said everything is okay if the matrix is symmetric. So if we would only have diffusive forces, we would have a symmetric stiffness matrix. That's all okay. So what I'm going to say here, I'm not really sure what happens in the general situation. I require that we are not so far away from the symmetric situation. And that is in this assumption that we have exactly the situation here. We have real eigenvalues and an orthonormal basis of eigenvectors. And under this assumption, we can prove this estimate, which tells us, okay, yeah, if this is really a sharp bound, it's not very good. This tells us the condition number is really pretty much increasing. It behaves, it's not only an estimate, it really tells us about the behavior. It behaves like h to the d. So the more we refine, the more critical the condition number becomes. Okay, maybe we prove this then next time.